Hi friends, Mechanics of Fluids in KTU syllabus in the third module ചില ഡീറ്റെയിൽഡ് ആയിട്ടുള്ള ഒരു എക്സ്പ്ലനേഷനാണ് നമ്മൾ ഈ വീഡിയോയിൽ ഉദ്ദേശിക്കുന്നത്. തേർഡ് മോഡ്യൂൾ നമ്മൾ നോക്കിക്കഴിഞ്ഞാൽ അവിടെ ബെർണോളിസ് ഇക്വേഷൻസും അതിൻ്റെ പ്രോബ്ലംസും ഒക്കെ നമ്മൾ ഡിസ്കസ് ചെയ്തതാണ്. അപ്പോൾ തന്നെ അതിൻ്റെ കൂട്ടത്തിലുള്ള അതുമായിട്ട് റിലേറ്റ് ചെയ്യുന്ന ചില ടേംസ് ഉണ്ട്. ഹെഡ്, പ്രഷർ, ഡൈനാമിക്, സ്റ്റാറ്റിക്, ടോട്ടൽ ഹെഡ്, ഇതുപോലെയുള്ള ടേംസിൻ്റെ ഒരു എക്സ്പ്ലനേഷൻ നമ്മൾ ജസ്റ്റ് നോക്കാൻ പോവുകയാണ്. അതുപോലെ തന്നെ ബെർണോളിസ് ഇക്വേഷൻ്റെ ഒരു വീഡിയോ പ്രസൻറ്റേഷനും നമുക്കിതോടൊപ്പം ഈ വീഡിയോയിൽ കാണാവുന്നതാണ്. ബെർണോളിസ് ഇക്വേഷൻ പഠിച്ച കൂട്ടത്തിൽ നമ്മൾ ഈ ഒരു ടേംസൊക്കെ ഒന്ന് കണ്ടതാണ്. അപ്പോൾ ഈ ഒരു വീഡിയോയ്ക്കകത്ത് നമ്മൾ കാണുന്നതിന് മുമ്പ് ഇതൊന്ന് മനസ്സിലാക്കുക. P/ρg എന്ന് പറയുന്നത് പ്രഷർ ഹെഡാണ്. V²/2g എന്ന് പറയുന്നത് കൈനറ്റിക് ഹെഡാണ്. അപ്പോൾ തന്നെ Z എന്ന് പറയുന്നത് പൊട്ടൻഷ്യൽ ഹെഡ്. അപ്പം ഈ പറയുന്ന മൂന്ന് ഹെഡും കൂടെ സമ്മപ്പ് ചെയ്യുന്നതിനാണ് ടോട്ടൽ ഹെഡ് എന്ന് പറയുന്നത്. ഓക്കെ.
From our school days, we have been taught and observed that spontaneously fluid flows from higher pressure region to lower pressure region. But what is the actual physics behind that? Now let's look into that phenomena more closely. Let's start with an example. Take a nozzle. At section A, pressure is P1 and velocity is V1. At section B, pressure is P2 and velocity is V2. Now, as particle moving from section A to section B, velocity of particle increases and pressure decreases. That means pressure at section A is higher than pressure at section B. Here, fluid flows from higher pressure region to lower pressure region, which is the obvious case. But now, look at the variation of flow properties and diffuser. Pressure at section A is P1, velocity is V1, and at section B, pressure is P2 and velocity is V2. As the particles moving from section A to section B, pressure increases and velocity decreases. Here, fluid flows from low pressure region to high pressure region. That is not the obvious case. Strange, isn't it? Actually, the pressures P1 and P2 which we are talking here in these examples are static pressure, and the statement spontaneously fluid flows from higher pressure region to lower pressure region is concerned with the total stagnation pressure, not the static pressure. So, total stagnation pressure at section A is always higher than the total stagnation pressure at section B, in case of nozzle as well as in case of diffuser. So, now the question is, what is the difference between static pressure and stagnation pressure? Let us understand these pressures with one funny example. Imagine that you have jumped into a pipe of sufficiently large diameter through which water is flowing. Now consider yourself to be moving with the flow of water with the same velocity of particles. Hence, there is no relative motion between your body and surrounding water particles. In this circumstance, the pressure that is experienced by your body is called static pressure. Now, imagine that during your travel within the pipe, one of your leg got stuck at some point, and now you are no more moving with the water. But water still keeps on moving with the same velocity and flows over your body. And hence, your body will experience higher pressure compared to the previous case. And this higher pressure is called stagnation pressure. Now, let's talk about the methods to measure these pressures. One way to measure static pressure would be to drill a hole in a flat surface and fasten a piezometer tube. And now consider a small tube inserted into the flow pointing upstream is called pitot tube. In each tube, the level of fluid indicates the intensity of pressure. The level of fluid in piezometer and pitot tube is same. Now, let us open gate from both the sides. particles moving from upstream to the downstream with some velocity v. As particle brought to the rest at the tip of pitot tube, the kinetic energy of particle is converted into pressure energy at tip of pitot tube. Fluid in the pitot tube, including the tip of pitot tube, will be stationary, and the pressure experienced at that point is called stagnation pressure. The pressure difference between stagnation pressure and static pressure is called dynamic pressure, and dynamic pressure is because of the kinetic energy of fluid.
This screencast is going to discuss a little bit about pressure, the types of pressure, how to convert from one to another, how to use them in calculations, and so forth. Just be a quick overview. So the first kind of pressure we're going to talk about, let's use a big tall glass of water and talk about fluid pressure. If we put a hole in that glass, then the pressure that fluid exerts would be equal to the pressure you would have to exert on a cork to fill that hole, right? So the forces counterbalance each other. And we know that pressure is a force over an area. There's many different units, but let's go with SI. We know that we could write force in newtons, and we'll just choose meters squared. And so very typically you can see a pressure in newtons per meter squared. That's also written as a Pascal. Other units you might see atmosphere, PSI, millimeters of mercury, bar, and of course pascals. The next type I want to mention is what's considered hydrostatic pressure. And that's the idea that this fluid has a weight to it. And so we're going to take whatever the pressure at the top of that water is and the weight of the water, add those pressures together, and then that gives us our hydrostatic pressure at the bottom. Typically, if this is open atmosphere, we'll refer to this as atmospheric pressure, maybe P naught, an initial pressure, and then the weight of the fluid. And so we'll write that as the total pressure here, the hydrostatic pressure is P naught, the fluid is rho GH. And you're probably wondering, how is rho GH a pressure, or does it have the same units? Right? If we write out rho GH, we know that it's a mass over a volume, and we're multiplying that by an acceleration and a height. And so we can see that the height over the volume, we get a mass times acceleration over an area. Mass times acceleration is a force, force over area is a pressure. And so those units do work out. And so that's how we calculate the hydrostatic pressure. Another type of pressure you're going to hear about is head pressure. And what that is if we create this hypothetical column of this water, and we just refer to that column, then we could call this water having a head pressure of whatever its height is. And therefore, we're going to refer to the head pressure as the height of the fluid, and that's regardless of the diameter of that fluid. It could be very large or very small. It's whatever height that column is. And so in this case, maybe it's 2 meters. And so we're going to say that this is 2 meters of water. And it's important to designate whatever fluid that is so that we could say that we have a hypothetical column of 2 meters of water, therefore that's the head pressure of the water. And we may want to convert that head pressure to a real pressure, like atmospheres or PSI, and I don't mean real necessarily, but something that you could maybe translate and compare to other systems. That case, again, is just going to be very similar to what we saw over here. And so it's the density of the fluid times gravity times the head of that fluid. That gives us whatever the pressure of that fluid is.
It is often convenient to represent the level of mechanical energy graphically, using heights, to facilitate visualization of the various terms of the Bernoulli equation. Each term in this equation has the dimension of length and represents some kind of head of a flowing fluid. First one is the pressure head. It represents the height of a fluid column that produces the static pressure. Let us visualize this pressure head in a more practical way. So for this, consider tiny fluid particles flowing inside a tube. This fluid particle creates pressure inside the tube. And if there is any hole, the water will leak because of pressure. But if we fit a piezometer tube here, the water will rise against gravity to a certain height, and by visualizing this height, we can easily calculate static pressure. Okay. Next term is called the velocity head, and we can easily visualize this with the help of pitot tube. When it is fitted, the water particles get trapped because of its small cross-section area and reduces the particle velocity to zero. This effect increases the water column to additional height, and this additional height is called the velocity or the dynamic head. Remember, this additional height is related with the velocity of water, and hence we call it velocity head. If flowing water have zero velocity or the water is not moving, then there is only static pressure head. So keep that in mind. Look! You have already visualized static and dynamic head on pitot tube. Now the last one is the elevation head. So, let's visualize it. Gravitational head is the height of a fluid particle placed above a selected datum. You can select datum anywhere, above or even below. In the end, it is just related with final value minus initial value, and value appears same whatever datum you choose. Now let us apply Bernoulli's equation in terms of head on two sides of the tube between point 1 and point 2. We choose the datum at point 1, so Z1 is 0. For water to flow in x direction, the pressure difference must be greater than 0. So static pressure P1 should be greater than P2. And finally, P2 is lower, so velocity V2 must be higher, because of low pressure and high velocity relationship, so velocity V2 is greater than V1. Did you notice? The whole Bernoulli's energy, that is total head for the flow, remains constant. And if you sum up every hands of left or right equations, you will always end up with total head, no matter which point you choose. Please subscribe for more fluid mechanics. Next topic will be about energy grade line and hydraulic grade line. So stay tuned.